let's investigate the properties of the trace. First, let's consider some coefficients alpha sub j. These are elements of the complex numbers. Let's also consider some matrices A sub j. These are elements of the n by n matrices with complex entries. So this fancy C denotes the complex numbers. We're going to be using these alpha sub j to scale the matrices. And let's start off by taking a linear combination of matrices. So we're going to apply the trace to the linear combination alpha 0, A0, plus alpha 1, A1. So this j over here is just a placeholder for an index. And we're going to use that to specify which coefficient and which matrix we're dealing with. So this is a linear combination of complex matrices. All of the entries in these matrices are complex numbers, and these are square matrices. They are n by n. So I'm writing n over here to keep it general. But if we were dealing with a qubit system, this would be 2 by 2. We would have 2 by 2 square matrices. Now, let's apply the trace to this linear combination of matrices. So first we can write out the definition of the trace in Dirac notation. So we can write this as the sum over some index k of the bracket sandwich between this k of this quantity. So inside the sandwich, I'm going to put alpha 0, A0, plus alpha 1, A1. And you can see that in this sandwich, we have a bra and a ket, and they are sandwiching this matrix over here. And what this does is it actually takes the sum of all of the diagonal elements. That is what the trace actually does. So if we were to evaluate this linear combination and get a matrix, then we would take the sum of all of the diagonal entries. And that is the quantity which we call the trace. So let's use this Dirac notation to break this up into several parts. So we can apply this sandwich individually to both of these matrices in the linear combination. And we can also pull out the complex coefficients. So that's going to give us alpha 0 times this sandwich of A0. And then we're going to have a similar object appearing for alpha 1. And then we're going to have the sandwich over this matrix A1. So what is this quantity over here? Well, that is the trace of A0, and this quantity is the trace of A1. So we can write this more condensedly as alpha 0 times the trace of A0 plus alpha 1 times the trace of A1. And this property we can call linearity. We could also separate this out and think of this as two separate properties. So one property allows us to take scalars, which are inside the trace, and factor them out. We're allowed to move those scalars outside of the trace. And another property here is this additive property. So if we have the sum of two matrices and we apply the trace, that's the same as individually applying the trace and then taking the sum. And if we combine those two properties together, we have this linearity property. So we can factor out scalars and we can split up sums. So this trace satisfies linearity. Another really important property that the trace satisfies involves the product of matrices. So now let's consider the product. So we're going to take the trace of the product of A0 and A1. So in general, matrix multiplication is non-commutative. That means if we swap the order of the matrices, we're going to get a different result in general. But what is really special about the trace is that if you apply the trace and swap the order of this matrix multiplication, it has no effect. So let's see why that's true. let's again write this out as a sum over some index, but now we're going to use index k0 because I'm going to be introducing another index as well. So we're going to sandwich this matrix product of A0, A1 in between this K0. So here we have a bra and then a ket. And now what I want to do is I'm going to add the identity operator. So I'll write it like this. We're going to have the sum over K0, and then I'm going to add another sum. And this sum is going to be over another index, and I'll call this index K1. And now I still need to have this sandwich over here, that is the trace. So I'm going to have K0, and then I'm going to have A0, but in between A0 and A1, I'm going to insert the identity operator. And I'm allowed to do that because the identity operator has no effect. So if I insert the identity in between these matrices, it's the same thing. So I'm going to express the identity operator as a ket-bra combination involving this index K1. And because I'm summing over all of the K1s, this object is the identity. One way to call this is the resolution of the identity. So now I'm going to complete this. So I'm going to have A1 over here. And finally, I'm going to have K0 in the form of a ket. So here we have a bra-ket sandwich, and we're summing over all K0. So that's going to give us the trace. And here we have a ket-bra combination, and that is the identity operator because we're summing over all K1 values. So now that we have this, we can group these objects differently. Now that's the beauty of Dirac notation. Dirac notation allows us to observe different things. If we group these guys together, we can see projectors. These are projectors that are getting summed up to form the identity operator. But if we instead focus on this combination and this combination, we can see that these are actually values. They are complex numbers. So here we have a vector, and we're applying a matrix to that vector, and then we also have a row vector on the other side. So this would be a column vector, and this would be a row vector. And if you sandwich a square matrix between a row vector and a column vector, you're going to get the result, which is a complex number. And this complex number satisfies commutativity. And because the complex numbers satisfy commutativity, we can swap the order of these two guys. And I'll write this all in the same color over here. So actually, I'll stick to purple for K1. So we're going to have the sum over K1, and then K1 is actually going to turn into this index that we're using for the trace. But I'll put this one in black over here. So we're still going to have K0. But now K0 is going to be used to construct the identity operator. So we're going to have K1 over here. That's going to be this term. And then in black, we're going to have A1. And in the middle, we're going to have K0 forming the ket-bra combination. So that's this K0 and this K0 over here. Then we're going to have A0. And then finally, we're going to finish off with K1 in the form of a ket. So look at what we've done over here. We have swapped the order of these two objects. So this is a complex number and this is a complex number. And this object used to be on the right, now it's on the left. And that means this bra and this ket over here are now forming a sandwich, and it's being summed over that index, which means this by definition is the trace. And what about this object in the middle that's formed from these K0s? This is now the identity operator. And because it's the identity, we can ignore it. So once we ignore the identity operator, we're actually going to get, write this in black, we're going to get the sum over K1. So we still have this K1 index over here. The sum over K1 of this sandwich between K1. And what's inside the sandwich is A1, A0. So we have A1 followed by A0. And then I'll finish off with this K1 ket. So now we've gotten rid of K0. That index is gone. because it was in the identity operator. And we're just left with this index k1. Now, this format is exactly the same format that we started with. The only difference is that we have a different index and the order has been swapped. So we've swapped the order of these matrices. That means we can actually write this as the trace of A1, A0. Now that is a fascinating property. We have swapped the order of the matrix multiplication inside the trace, and it has no effect. These are equivalent. And how have we proved that? Well, we've expressed the trace in terms of Dirac notation, and we used the resolution of the identity. We inserted the identity in between, and that allowed us to swap terms and show this property. A property that is a consequence of both of these properties is actually the trace of the commutator. So let's take the trace of the commutator. And I'll write that over here. So we're going to take the trace of the commutator of A0 and A1. So by definition, the commutator is, I'll write this inside the trace, is A0, A1 minus A1, A0. So this is by definition the commutator. When you put these square brackets with a comma over here, that is shorthand notation for this combination, where we swap the order and then subtract. But because we have this linearity property, we can break this up. We can break this up into the trace of A0, A1 minus the trace of A1, A0. So you can think of this as a linear combination where the coefficient over here is -1 and the coefficient over here is +1. So this alpha 1 would be -1 and alpha 0 would be +1. And A0 is actually this combination A0, A1, and A1 is this combination A1, A0. So when you evaluate these guys together, they will form a matrix. So we'll have a square matrix and a square matrix. So what we've done is use the property of linearity to split this up. And now we can use this property that we proved over here to state that this quantity and this quantity are equivalent. So that means these guys are equivalent and we're subtracting the same quantity. That means this evaluates to 0. So the trace of this commutator of matrices is equal to 0. Another interesting property of the trace is that the trace of some matrix A is equal to the trace of A transpose. Now, why is that true? Well, when we evaluate the trace, we're taking the sum of all of the diagonal entries. And the diagonal does not change when you take the transpose of a matrix. So that's why A and A transpose, they have the exact same trace. So when you take the transpose, all of the off-diagonal entries, they get swapped over. So you're reflecting the entire matrix over the diagonal. But the part of the matrix that remains unchanged is the diagonal. So all of those entries remain the same. And that means the sum of those entries also remains the same. So this is a very important property as well. And now what I want to do is generalize this property to the product of 3 matrices. So that's what we're going to do down here. We're going to take the product of 3 matrices. So let's have a look at what that's going to look like. So we're going to have the trace of A0, A1, A2. This is a triple matrix product. And because of the associative property of matrix multiplication, you can evaluate this product first or this product first. It doesn't matter. So you can first multiply A0, A1, and then multiply the result with A2, or you can multiply A1, A2, and then take that result and multiply it with A0. But what's really important is commutativity is not satisfied by matrix multiplication. But there is a property that will be satisfied. So in general, you're not allowed to swap the order in any form, but you are allowed to do cyclic permutations. And we're going to see why these cyclic permutations work. So first, let's express this in the same form that we had over here. We're going to need 3 indices. And those 3 indices are going to be K0, K1, and K2. First, we're going to use K0 to construct the trace. So we're going to have a bra version of K0. Then we're going to put A0 over here. Then we're going to insert the identity, and we'll construct the identity using the index K1. Then we're going to have A1, and then we'll insert another identity with K2. And finally, we'll finish off with A2. And over here, we're going to need a ket of K0. So what is K0 doing over here? K0 is being used to construct the trace. And we're summing over K0, and that gives us the trace. And this K1 and K2 combination over here, this ket bra and ket bra, these are projectors. And because we're summing over all values of these indices, these guys are the resolution of the identity. So we've inserted the identity operator between A0 and A1, and we've also inserted the identity operator between A1 and A2. Now, what we can do is observe that these guys are complex numbers. So we have 3 complex numbers. That means we can swap the order. So let's move this complex number from the end to the front. So we'll do a cyclic permutation. And if we do that, we're going to get the following combination. So we're going to take this K2 and put it over here. Then we're going to have A2, and then we're going to have K0 in a ket bra combination, followed by A0, and then we're going to have K1. So this K1 over here in a ket bra combination. And finally, we'll have A1, and A1 is going to have K2 on its right. So can you see what's going on here? All we've done is we've moved this object to the front, and we've just slided these guys over to the right. So now K2, so now we still have these 3 sums over here. So this K2 is now playing the role of the index for the trace. So we're using K2 to construct the trace, and we're using K0 and K1 to construct these identity operators. So if we ignore this identity and this identity, we will just see this matrix product A2, A0, A1 occurring within the trace. So we can write this equivalently as the trace of A2, A0, A1. So we have A2, A0, A1. And let's do this one more time. So let's write this as the sum over these 3 indices. We need these 3 sums. And let's move this one at the end up to the front. That's going to give us K1, A1, K2 in a ket bra combination. So this K2 pairs up with this K2. And then we have A2, and then a ket bra of K0. And finally, we have A0, and to its right, we have K1. So now K1 is being used to construct the trace, and K2 and K0, these are being used to construct the identity operators. So here we have 1, 2, and 0. And if we ignore this identity and this identity, we're just going to get the trace over this index K1 of A1, A2, A0. So I'll write that over here. We're going to get the trace of A1, A2, A0. So would this work if we took this combination in the middle and tried to move it over to the left or to the right? Well, it would not work. That's because the indices do not match. So if you took this one in the middle, this K0 does not match with this K1. And what if we took it over here on this side? This K2 does not match with this K1. You need the indices to match so that you can identify the identity operator. There have to be these projectors over here, and these projectors need to have the same index in both places. So only cyclic permutations are allowed. And I'll write these cyclic permutations out over here. So we start off with 0, 1, 2. That's the first of these cyclic permutations. Then we go over to 2, 0, 1. That's the second. And then we have 1, 2, 0. And if we were to do this permutation again, if we move this object up to the front, what would happen? Well, then we would have A0 out the front, and then we would have 1, 2. So we would have 0, 1, 2, and we're back to where we started. So there's only 3 combinations in this cyclic permutation. You're allowed to do cyclic permutations, but any permutations that don't fit this pattern are not allowed. They are not equivalent. Why are they not equivalent? Well, it's because we can't construct identity operators using this Dirac notation. So in general, they're not equivalent. You may find special cases where the matrix product is commutative and you're allowed to swap them around. But in general, that property does not hold. The property only holds for cyclic permutations. So in this video, we saw some very important properties that are associated with the trace of matrices. We saw this property of linearity. We saw this symmetric property where you can swap the order of matrices when you're multiplying them inside the trace. We saw what happens when you take the trace of a commutator. We saw what happens when you take the trace of the transpose of a matrix. There's no difference. And we also saw this cyclic property that is associated with the product of matrices inside the trace. So all of these are essential properties that are very important in understanding quantum mechanics. The trace appears in many equations in quantum mechanics, and we're going to be using this trace in lots of videos in the quantum mechanics playlist.